the question was related to negative Poisson's ratio. Materials which have that property are typically called as auxetic materials. And you're absolutely right that from wherever you have seen that, these are being considered for high impact kind of applications where the energy absorption is the main key criteria in selecting a material. You have to actually go write the expression for the strain energy, which takes into account the strains occurring both in the direction in which the load is applied and the perpendicular directions as well. And there you would see that if you actually do a calculation, and you can even do this and plot it versus nu for a given value of E, you can have some kind of a non-dimensionalization of the energy, strain energy, which is nothing but half of your, let me write that. So you would have the strain energy density, which is the energy per unit volume. Let's say in SI units, it's joules per meter cube. This is going to be given by 1/2 of your. Yes, correct. So writing purely in terms of the strain, let's say gamma transpose into the stiffness into gamma, where gamma is the strain. So what he's telling is right that yes, sigma is nothing but sigma. So that's what he was referring to as sigma times gamma, right? Now, once you do that, you know that this is having multiple terms there. So it has, let's forget the shear for now. So suppose you even take just the normal strains, because in isotropic material, they're not coupled with each other. So what you're looking at is gamma 11, gamma 22, and gamma 33 will be zeros essentially for this particular kind of loading that you're looking at. So once you do that, you'll have a 3x3 matrix that of this 6x6 matrix. You'll take that you'll partition and take that 3x3 matrix at the top left, and then you will multiply this. When you do that with the negative Poisson's ratio, you would actually see that this is the total strain energy density. So for a given unit volume, this would be the energy. So because you'll essentially, to get the total energy, you'll be integrating this with respect to dV, which will essentially be a volume integral over any particular volume that you're looking at. So when you do that, you would see that this can be written as a function of the Poisson's ratio nu. Okay, and then you can plot for the entire range, let's say U versus nu, and then you could start with, let's say, -1 and all the way up to 0.5. Right? So when you do that, you will see where it actually peaks. Okay, so let this be a homework, why not? So, let this be an assignment. So assignment number 2. That you can submit by next Friday. It's, I think I've given most of the answers, so it's fairly straightforward. So what you're essentially looking at is that, as he said, you will have to go to your sigma, because that's how the two are related. The Poisson's ratio will actually come through that. So your S will be in terms of the Young's modulus and the Poisson's ratio. So for a given Young's modulus, you can actually plot this. Some way you can non-dimensionalize this to plot versus nu, or you could plot it in absolute terms as a for a given value of E, right? Young's modulus, and then you will see where it actually peaks. So that will give you an idea of whether it is good for impact. So this is actually a very preliminary way of looking at it, because impact is much more involved. So we are not actually getting into those aspects. So let's say from this strain energy, purely strain energy, because this is valid even for static problem, leave alone impact or any dynamics problem, it's valid for a statics problem that you're looking at. But essentially you're seeing that how does the change in nu contribute. So your intuition, I kind of can see in parallel with it, because what you're saying is that in a negative Poisson's ratio material, when you're trying to extend it in another direction, it's getting extended in the other directions as well. Now remember that the strain energy is blind to whether it's a tension or a compression, okay? Unless, of course, the stiffness itself varies in tension and compression, it doesn't care whether it is tension or compression, as long as there's a particular value of strain, because it's quadratic, you see. So it's quadratic in the strains. So whether it is positive or negative, it doesn't matter. So it will just multiply and give you. So on this side, you're going only up to 0.5, whereas here you are extending it all the way up to -1. Again, depends on the kind of material, particular material, whether what actual value of Poisson's ratio it has, but the possibility of pushing it more so that there's much more deformation in the other direction, which is also going to contribute towards the strain energy. So the strain energy is not only the direct contribution of whichever direction you're applying the load, but there is the strain happening in the other directions, which also contributing to the strain energy. So you're seeing how you can kind of maximize that absorption of the strain energy, right? So as I said, this is a very simplistic way of looking at problems, but we will take it for now because we are in the initial stages of this course. Yeah. Okay, so I think we'll get started. Yeah. Uh-huh.
The cross-sectional area keeps increasing, and does the load carrying capability of such a material keep increasing?
No. Because see, we again are talking about certain assumptions that are involved, that the Young's modulus doesn't change as once the expansion in the other directions goes beyond a certain point, there's a possibility of the Young's modulus changing as well. So in other words, it will be a nonlinear kind of a behavior, okay? Again, we are talking in very generic terms. There's a lot of difference material to material. There are different types of negative Poisson's ratio materials that are there. Most of them are not inherently at the, let's say, the atomic level, they are not negative Poisson's ratio, but the way the atoms arrange themselves or molecules arrange themselves, there's a certain specific geometry that they get into, and geometry is what enables that. One of the very simple geometries that does this is an inverted M kind of thing with, suppose these all constitute particular points in the material, could be molecules or atoms or whatever you have. So in this kind of a geometry, it could be either the crystalline geometry or a polymer monomer within a polymer kind of a geometry. But essentially what happens when you apply a tensile load to this, let's say some force F you're applying, you can very easily see that overall there is an increase in the other direction. Whereas the typical conventional Poisson's ratios of around 0.3 for metals that you're typically used to, you would see that when you pull here, you're expecting this also to contract. But because of the basic structure that it has, it can undergo a negative thing. So depending on the actual, this is one example, there could be many other examples. How far you stretch that will actually depend upon this particular configuration, the bond strengths that are there, etc. So the material science people will go into more depth in terms of understanding it from that level. So we as structures people, we are not so much focused on that. Given a particular Poisson's ratio for a particular configuration, we can go forward and see how to apply it to an impact mechanics problem, or where the impact load is one of the dominant loads, and see how we can maximize the energy absorption. Right? Anybody else? Any questions? Okay. So we completed, I think, 5 of these, right? So the last, we finished that also? Yeah. Okay. Yeah. Okay. So flight phase, it's quite straightforward to see that depending upon the particular flight phase that the aircraft is in, if it is an aircraft, otherwise it could be a launch vehicle or a re-entry vehicle, etc. It could have certain things changing in this in terms of what is involved. But essentially for each one of those phases, you know the kind of maximum load factors that this will go to, the maximum speeds that it will go to, and based on that, the load is actually determined. So I think I've been mentioning earlier also, there's the something called design limit load, the design ultimate load. And the design limit load is essentially in terms of N max. What is the maximum load factor that it can go to. That is essentially your L by W, where lift L is lift and weight, W is the weight. So you're talking of that maximum value that you're looking at. That's what you call as the design limit load. So for different structural components, they might experience something slightly different, because one is for the aircraft you're defining this, and based on the aircraft, within the aircraft, most people in flight mechanics, for example, you consider the entire aircraft as a rigid body and you'll deal with it. So all structural components exposed to the same in. But in a structural mechanics problem, there are parts of the structure which are vibrating with respect to each other, and therefore there's a certain level of acceleration that gets added to it. It's a very small delta n that is associated with it. So you'll have to account for that also in particular structural components over and above the whatever you have for the aircraft within the structure. So it's two sets of references that you're talking about. One which is fixed to the CG of the aircraft, and you consider the entire aircraft as a rigid body. You do the typical flight mechanics problem, and one based on that, you arrive at the kind of flight envelope, and therefore from that the N max. But then over and above that, now you relax the aircraft, which you assume to be rigid, now to be actually a flexible structure, and therefore it can undergo vibrations, and vibrations will result in certain level of acceleration with respect to the CG of the aircraft, and that has to be taken into account as well. Compared to, of course, because what we are non-dimensionalizing with respect to is the weight of the aircraft, and structural component, each structural component will be very, very small mass compared to the mass of the aircraft, and therefore it may not be a very large difference, but there could be certain parts. For example, you take the, let's say the turbine blade or the compressor blade or the fan blade or a propeller, or in a helicopter, the rotor blade, then you could have large differences cropping in because of that. So there are certain parts where that is important. So you can't just go with the N max of the aircraft. And then you typically define your design ultimate as the factor of safety, let's say about 1.5 times your DLL. So this is when you say it's in N, it's typically expressed in terms of the acceleration due to gravity on the Earth's surface, g, small g, 9.81 meter per second squared. So in terms of that, it is expressed, and then your this is the DUL, or design ultimate load, for which you're actually designing the entire structural component, all the structural components of the aircraft. So yeah. So what I was saying was with respect to the flight phase. So depending upon which flight phase it is, in the N max of the aircraft will vary, and therefore you'll have to take into account all of those. And there might be certain components which are more designed based on a maneuver, certain others which could be based on landing, for example, the landing gear, etc. So you'll have to take into account all of those things. Next, so the last thing is geometry. Last but not the least, because geometry, many people tend to kind of ignore it or give it less importance than what is due to it. Truly speaking, geometry plays almost the same level of importance as the material in terms of deciding the overall design. And as we saw in the distinction between the civil engineering structures and the aerospace or any vehicular structures for matter, there's a lot of difference, not only in terms of the material choices, which are based on your sigma u by rho and e by rho, etc. Whereas the geometry, it's in terms of going for thinner and thinner geometries. But even if you look at it, even civil engineering structures, though we try to make a big difference out of it, if you look at this beam, for example, the length is very large compared to its width and height that you see. Similarly, if you take the floor slab that you have over there, either the one at the bottom or the top, you're essentially seeing that if you compare to the dimensions of this room, which is the length and the breadth, the thickness of the slab is actually small. So in other words, that's also a plate. Essentially, this is also a beam. So in other words, we are dealing with these kinds of structures, that is 1D or 2D structures. As I mentioned earlier, everything is in reality 3D, just that from mathematical perspective, to make things simpler, we take advantage of the fact that certain things are smaller compared to something else, or certain things are larger compared to something else. So we can drop off what are known as the higher order terms, so that we are dealing with a much simpler model. So for example, when you're expanding this out, you have that 3 by 3 matrix, you have these strains, so you have so many different terms. So depending upon, so this is a generic problem we're talking about, but if it's a beam or a plate, we will take advantage of the fact that not all of the terms after this expansion will be of equal importance. Some will be much larger in size, quantity compared to the others, and so we retain them and drop off the higher order terms, so that we might still get almost as accurate a solution as possible as you would if you take everything into account, just that your computational efficiency will improve quite a bit by dropping off those terms. And this is a simple problem, but when you go to more and more complex problems, when you have all the terms, you may not even be able to solve that with the kind of math or computational capabilities that you have. So the only way to solve them perhaps would be when you use the fact that there are certain small parameters associated with the very problem definition. And yeah, as we saw here also, you have plates and beams, just that these are solid, whereas in most cases there we might have hollow. Even when you have certain hollow cases, like for example these days hollow bricks are very common in civilian constructions, still the thickness to the overall width or length of that brick, for example, would still be much larger compared to the thin-walled cross-sectional geometries that you would have over here. So the thicknesses are much smaller, and therefore there's a deformation that is happening within the cross-section. So the cross-section, so like what you talked about, what about the change in E that is happening because of negative Poisson's ratio material undergoing some expansion in the other direction when there's tension in the main direction? Even when you don't have a negative Poisson's ratio material, you could have situations where, because of the thin-walled geometry, the thin-walled cross-sectional shape will be entirely different once the loading starts, and there's a certain amount of strain energy which goes into the deformation of the cross-section apart from the overall deformation of the beam or the plate, reference line or reference curve, or the reference surface, and then you would have to take that into account otherwise you will end up with very, very different results from what you would observe in experiment or in a flight test or through sensor measurements. So coming to the geometry, as I said, it plays a very, very critical role in terms of the choices that you make. So you have the one-dimensional geometries, which typically people again classify into ties, struts, struts sometimes called as columns. Then you have the rods, which is another name for ties, especially when it's instead of a cable or a wire kind of a thing, it's actually a solid. So you have rods. And those are the only two things which you'll typically consider in the kind of designs that the Wright brothers went for, and later on what we call as the truss structures. In trusses, you typically have these rods, and you would have along the length of the fuselage, if it's a fuselage that you're talking about, or the span of the wing, you would have rods which are running through the length, which are typically called as the longerons. And then you would have certain horizontal vertical members which are connecting to each other, and also some diagonal members which are essentially transferring the load from one to the other, tension and compression that you typically have. Going beyond that was in the form of frames, so that truss structure essentially could be considered as a frame. So there could be much simpler frames as well, where, for example, just a cross-section of a beam along, let's say, the cross-section of the wing for that matter. Many times we'll be referring to the wing as a beam, though more accurately it's the spar or a longeron or a particular stringer which you have to consider as a beam. But for an initial cut analysis, you can treat the entire wing as a beam. So what kind of boundary conditions you think wing has, typical fixed wing aircraft? Cantilever, right? So essentially the end which is attached to the fuselage, irrespective of how that attachment actually is, how complicated it is, relatively speaking, it is like a fixed end. In other words, the deflections are zero and the rotations are also zero. So you essentially have a fixed end kind of a boundary condition. The other end obviously is a free end, where there could be free vortices, etc. But whatever the load might be in terms of the actual end conditions, it is a free end. You had a question? Okay. So what about the fuselage? Can you treat the fuselage as a beam? Initial cut analysis, just like however crude considering the entire half of a wing as a cantilever, is it possible to consider a long fuselage as a beam? Okay, yeah. Yeah, so that's also true for the wing, that you might not have it fully filled in a solid way. You might still have a thin skin that is there, but you still can consider that as a beam, right? So as you said, in the case of the fuselage also, it's a thin skin. You could have formers and bulkheads at different locations, also longerons and stringers. But whatever it is, it is a long structure. So because the way we define these 1D and 2D structures, I repeat, is that you consider one dimension much larger than compared to the other two, you call it a 1D structure. Another one dimension is very small compared to the other two, you call it a two-dimensional structure. And as I said, we have to be a little careful when we move to dynamics and we not consider the actual lengths, especially the larger one. You have to consider the wavelengths, the dominant wavelengths of deformation. So whichever modes of vibration are dominant, you have to consider those wavelengths. Compared to that, you have to look at the cross-sectional dimensions of a beam or the thickness of a plate or a shell, right? So that being the case, can you consider the fuselage as a beam? Hollow beam nonetheless, as you said, but can we consider it as a beam? Yeah? Okay, what about the boundary conditions for the cantilever? Huh? Free, okay, good. As far as the two ends of the fuselage are concerned, still covered? So let's say this is essentially the fuselage. So what you're saying is that the nose of the fuselage and the tail cone that you have essentially free, right? So it's a free beam. But what about the things which are attached to it? There's the wing and there's the empennage. By empennage I mean the vertical and horizontal stabilizers put together. Yeah, okay. Only moments, or will they? Yeah. So essentially at those points where the beam is, in this particular fuselage beam, is attached to the wing, you are saying that there could be a force that is there and there could be a moment that is there. Similarly, much smaller force and let's say a much smaller moment at this point, but once you transfer this to that location, because of this force and even though it is small, the moment arm is large, so that the moment due to that will be comparable. But right here, the moment which comes to it might be small or even zero, because you typically will have symmetric airfoil cross sections for the horizontal tail, whereas you will have cambered ones typically for the wing. Now, what does this, so is this one way to look at it is as a free beam, which is having these two as the applied loads, right? Whatever is coming through the attachment of the wing and the empennage to the fuselage, that is coming as loads. But another way of looking at it is, instead of drawing it that way, so instead of this, you can think of it as an attachment that it sits on. So it's like a simply supported beam, but with an overhang. So in other words, it's extending beyond this particular location. Yes? Yeah, that's correct. That's correct. Yeah. That's correct. That's correct. So what we are looking at is in this plane. Similarly, in the other plane also, you would have the support that is there. So typically, when you draw the shear force diagram, bending moment diagrams of simple problems, you're doing a planar problem, but you can do it in two separate ways if it's a linear problem, and then you essentially add. So it's in the other direction that you would have a, yeah, absolutely right, yeah. So another question that can arise is, typically once you put it on rollers, you're of course allowing for this expansion to happen, which can generally be possible, but it cannot create any moments. So whereas it is in general possible for the tail to be generating certain moments at that location as well. But as I told you earlier, typically for most conventional aircraft, you would have a symmetric airfoil cross section, and therefore the moment contribution of that at that location will be negligible, and therefore this is sometimes taken as a reasonably good first approximation to get you ballpark values in terms of how the bending moment distribution, the shear force distribution are through the length, and then you will go for more and more accurate ways of estimating that. So the 2D models that we're talking about not only valid for the structural components, but for the major parts of the aircraft itself. We saw the wing or tail as a cantilever, and the fuselage as a simply supported beam with overhangs, because it's not ending at the supports, it's going beyond the supports as well, so we call it a overhang. So similar to what you would have like a surja on the window, which is essentially an overhang that you have. But of course, there you can treat it more as a clamped end, fixed end, and therefore you can think of it as a cantilever. But you can think of in buildings also various designs in which certain structured component extends beyond the point of attachment, and therefore you treat it as an overhang. So coming to the rods, as I've been repeatedly stressing, we take into account not only the forces, that is the axial loads, but also the moments, which means that beams also become a part of this 1D, and the other moment, which is the torsional moment, typically what is called as a torque tube or a shaft, that becomes a part of it as well. And pipes, as you mentioned, in the fuselage, as internal pressurization, and therefore that's one kind of load, like a pressure vessel, that is taken into account as well over there. Coming to the 2D, when there is no initial curvature, you call it a plate. I mean, there is initial curvature, you call it shell, and all the skin of the lifting surfaces as well as the fuselage are essentially shell-like structures, typically smaller sized panels which could be attached to each other, but we are moving slowly towards larger and larger panels, and sometimes integrally manufacturing or co-curing them as well, especially with composites. And again, you could have either solid or hollow. In the case of the beams, for example, you could have thin-walled beams, you could have thick-walled beams. Certain locations where the transverse shear is very large, you would, instead of going for thin-walled cross-sections, may have to go for, relatively speaking, thicker-walled cross-sections. Then again, in terms of the cross-sectional shape, you could have certain symmetries, either in two orthogonal directions or just one of the directions. Like for example, an I section could be symmetric in both directions, or if the flange lengths are different, the two flange lengths, you could have symmetry in one of the directions, which is the vertical direction. Similarly, you could have entirely asymmetric sections, and you could have some axisymmetric sections like a circular tube, etc. And in all of those cases, once again, you could have either closed sections or open sections like channels or T section, or you could have an, let's say, Z section or star section, etc. So many different possibilities are there. There are also a lot of things based on the design experience of different particular companies. They tend to prefer one over the other. It's not that it's a sacrosanct decision, just that they might have all of their production, manufacturing catered towards that, and they might have earlier designs which are proven, and they want to probably continue with that when they go for a new aircraft. So some of these decisions are based on that, because purely from the structural point of view, sometimes they may not be too much of difference going between one type to the other, as long as you are ensuring the level of stiffness required, the level of strength required for each one of these cases. So I think with that we have kind of completed this. Any questions on this geometry? Because we'll take up the geometry in little more detail now. Okay. Okay. So we have, you will also look, before we get into the geometry, we'll also look at the load source types in a little more detail, both from the point of view of where they arise from, which is what the source means, but also in terms of how they are reacted to, because there's a certain level of reaction that the structural component is offering when you load it, and that reaction is what we typically call in the form of stresses and or integrated forms of that stresses in the form of let's say shear forces or bending moments, etc., after appropriate multiplications and integrations. Then the more important thing, hopefully we cover a part of that today, is the typical construction geometries that are used in flight vehicles for structural components. Okay. So now coming to the sources, the loads on flight vehicle structures, again, is just formally stating things that we have been discussing in pieces here and there. The main source, of course, is going to be your airflow, and from the airflow, the main kind of load is going to be the lift, which is essentially an integration of the pressure distribution at the bottom. Subtract that from the integration of the pressure distribution on the top, so you end up with that lift. Similarly, in terms of the pressure drag, because there can be other drags like the skin friction drag and the wave drag, etc. The pressure drag is essentially you're integrating the pressures in the front end and then subtracting it from the rear end. So that is the next most important. Then typically you have the pitching moment. That is the third most important thing. Again, an integration of the pressure distributions and or shear distributions, but multiplied with the moment arm with respect to whichever point you're taking the moment, typically the CG of the aircraft. So you would want to multiply by that moment arm of the distribution and then integrate it. So you end up with the pitching moment. Then you would also similarly, you can think of the rolling moment, the yawing moment, and sometimes a slight sideway drift that can happen, typically in a gust kind of a situation. So, and for helicopters, of course, that could be one of the important things to be considering as well. So all of those are typically known not only in the form of the resultants, which is what is important in a flight and space mechanics kind of a problem, but in flight vehicle structures, the actual distribution is also very important for us, because we are interested in designing specific structural components over there, and that is possible only when we know the actual distributions rather than the resultants. So we'll talk about the resultants later, but the actual distributions play a very, very critical role. Then coming to the concentrated loads, as I mentioned in the last class, there's no such thing in reality as a concentrated load, just like there's no such thing as a 1D or a 2D body, just that it's a mathematical simplification that we are going to, wherever we, without loss of much accuracy, we can have enhanced computational efficiency. So similarly, the concentrated load is actually, for example, if we say that the engine loads, the thrust as well as the self-weight of the engine, is a concentrated load acting on whichever the attachment point could be. It could be sometimes on the fuselage, sometimes on the wing. So wherever it is attached, it's almost like a concentrated load. But in reality, the way it is attached to the aircraft, through the appropriate pylons, etc. So the attachment mechanism that you have, that will play a critical role in distribution over there. But compared to many other distributed loads, this will be very large intensity, and therefore for the first cut analysis you might treat it as a concentrated load. Then concentrated loads also come due to the landing gear apart from the engine. So the landing gear again could be of many different types. Typically you would have the tricycle kind of a thing in many configurations, where you have a nose wheel and then two more wheels at the rear. So many times for larger aircraft it's on the below the wings. And you could also have some cases, let's say amphibious aircraft, you could have float kind of landing gears. So you could have skid landing gears in helicopters, very commonly used. So depending upon the actual landing gear design, the load distribution there also is quite different. And typically, we are interested in the contact mechanics of the tire with the tarmac of the runway, and then also this friction that is there, and different kinds of surfaces that it might be landing on. And on the same surface, where if it's a dry surface or a wet surface, etc. So based on all of these things, there would be slight differences. So all of that would have to be accounted as well. Then coming to the impact, we saw bird hits, for example, or a tool drop, etc. There could be other kinds of impact as well that one needs to look at. The landing itself is in essence an impact that is actually happening, depending on sometimes if it's a very rough landing, the impact loads of that has to be really considered in the overall design, especially of the landing gear struts, but also the part of the fuselage or the wing to which that landing gear strut is in turn attached, because there's a whole lot of importance that we need to give for the load transfer process. One is the load estimation, the overall load, the load distribution, but also the transfer, because we are not using a single structural component, we're using multiple structural components. They're all attached to each other, various types of joints, and how that load gets transferred from one component to another is very important. When we say, for example, a load is shared between two adjacent components, more often it may not be that the sum of the loads of those two components is equal to the original load, because it might be in a series and the entire load will be transferred, but just that the first structural component which is experiencing the load, for example, the skin of the aircraft which is experiencing the air loads first, might deform to some extent and therefore absorb a certain amount of the energy of the work done by the air loads, and then transfer the remaining part of the energy to the components that it is attached to, let's say the spar, or then the spar in turn to, let's say, the ribs, and the ribs in turn to the stringers, etc. So that load transfer process, many times you might see that the actual load, the entire load which came first is getting transferred, but you might see what is the role of that then. But actually there's some amount of energy which is getting absorbed as you go from one component to the other in this path of the load transfer that is very, very important to understand as well. And then, of course, the controls. Most often the controls are in the form of your elevators, rudders, and ailerons, and therefore they are essentially part of the airflow a lot of times. So there are two ways of considering that. Either you can think of that as an additional load over and above the configuration where these are not deflected, the control surfaces are not at all deflected, that you take as the airflow, and then the additional moment or force that comes because of either a rudder deflection or an elevator deflection or an aileron deflection, you treat that as an additional concentrated load that is coming. Another approach to this, which some people take, is in terms of, because those control surfaces are all aerodynamic surfaces anyway, you treat that as a different flight phase in which those are deflected at different levels, and then based on that you recalculate the airflow and therefore the air load distribution that you have. Then the self-weight, again, in a flight mechanics course, the actual weights, you might be lumping them. So a lumped weight kind of approach might be good enough, but in structural design, it's very important the actual weight distribution of the different materials used, and therefore their densities, their volumes, and therefore how their self-weight is coming. And we discussed in an earlier class in terms of the certain things which are disposable, like for example your fuel. As the fuel gets depleted over the flight, how that is actually utilized. For example, if you have fuel tanks, let's say in both the fuselage as well as the wings, you would which do you think you want to utilize first as you fly? Which fuel tanks would you want to empty first? Wing. Why?
We prefer fuel to be near the CT wherever.
Okay, but it's still equally distributed on either of the wings, right? So that's not really an issue. It's a good thought process, though.
The moment comes down.
Yes.
It's the wing. At the attachment point, there's a huge moment.
Uh-huh.
We reduce the weight.
Yeah.
The moment comes down, there's no fuel on the wing.
Okay, but what is the major moment actually,
The lift.
right?
The lifts will not be compromised if the fuel in the wings are depleted, gravity reduces, so that will not compromise
So,
on the wings.
so which would you want to deplete first? I'll come to you. And which would you want to deplete first, the fuselage tanks or the wing tanks? Wings, yeah.
Fuselage will empty first so that the moment due to lift and on the wings,
Uh-huh.
whatever moment is coming due to lift, part of it will be cancelled due to the fuel weight. So it will not.
Very good. Yes, that's the answer. So you typically would want to, if you have fuel tanks on both the fuselage as well as the wings, as she said, you would want to empty the fuselage first, because the fuel in the wings typically will bring a downward force, and that is compensating for the moment which is coming from the lift. Lift distribution is trying to bend it upwards. The fuel tank weight is trying to bring it downwards. So it's actually an advantage to have the fuel tanks full on the wings. But yes, there might be certain mission-based requirements because of which sometimes the other thing can be done. But purely from a structural point of view, if you want to extend the life of the wings and the attachment points in particular to the fuselage, you would typically want to go this approach where, yeah.
Sir, if we use fuel from the fuselage first, then won't the CG shift a lot? And this will bring control problems again.
Yeah, so that has to be, of course, taken in the design in terms of where you locate the fuel tank in the fuselage and how it's actually getting depleted. Typically, whether it's in the wing or in the fuselage, you will not have it all in a single tank, unless it's a very small aircraft. For typical large aircraft, you would have some kind of compartmentalization there also, and the rate at which it is getting dispersed from the different tanks will be controlled. So there's some calculations which goes into that, but that's a very important point that you brought out, that has to be taken into account. Otherwise, the shift in CG could be so large that your stability and controllability can be affected by that. Yes. Yeah, okay. So that's as far as the self weight is concerned. Then especially when you're using composites, the effects of the humidity and the temperature can play a bigger role than it would in the case of metallic aircraft. Metallic aircraft, there is a susceptibility to corrosion and things like that. So from that point of view, this could be of concern. For example, some of the aircraft which are operated during desert storm, for example, were affected by the saline water environment over there and the high humidity levels, and the corrosions were much more than typical in such operations. But once you go to there's no corrosion as much unless there's particular materials are used as part of the fiber and the matrix. But for the typical composites like carbon epoxy or glass epoxy, etc., more often it is the thermal stresses and the hygrothermal stresses that develop. Hygrothermal means that the stresses from the humidity as well as the temperature differences or change over a period of time, or in a spatial sense, a particular part of the component is exposed to a certain level of temperature, another end of it is exposed to, let's say, a very different temperature, then over a period of time that can cause problems. In the case of metals, creep will be a very important problem, and when we go to metal matrix composites, that kind of carries over as well. And so that's something that needs to be taken into account over a longer period of time, what actually happens in terms of the degradation in the properties. But there are ways to overcome some of those things. When we visit the specific materials for the fibers and matrices, we'll probably talk about that in a little more detail. Then coming to engine thrust, I think we already discussed that. Then coming to the inertial and gust flow, and sometimes there could be thrust vectoring and things like that. You have to obviously account for all those changes, not only in the magnitude of the thrust that the pilot can control, but also in terms of the direction of the thrust. So it's both because it's a force, both the magnitude and the direction plays a critical role. And also when you have multiple engines and one of the engines fails and you're applying one of the control surfaces in order to balance the moments, so those kinds of conditions are also typically accounted for in the overall structural design. Then the inertial loads, essentially your DLL and therefore DUL are coming from that difference that you have in the lift and the weight, how they are as a ratio different from each other. And typically you're, even when you're flying in a cruise-like condition, there can be gusts that are happening, and those cause inertial forces because you're essentially talking about a change that is happening in the overall acceleration levels. It could be either the translational accelerations in the different directions or also the rotational accelerations, what you call as angular acceleration, multiplied by the corresponding moments of inertia or products of inertia that are there. You would get the inertial moments. So when we talk of loads, we are generally talking about both forces as well as moments that could arise. Then the last you mentioned just a few minutes back, internal pressurization. So typically most of the aircraft these days are flying at about, let's say, 10, 11 kilometers. The kind of pressure levels at that are not suitable for human beings to be in, especially for that long duration. Even for short duration, it is difficult for most average human beings to survive on that. And because of which an internal pressurization is created, but not at the sea level values, because that will create huge amount of stress in the structure, and therefore you would require much thicker skins, and therefore the structural weight penalty that you would have to maintain sea level pressures even at the cruise altitude will be very large. So typically you will have let's say about 60 to 70% of that is what you typically have. The newer aircraft are coming up, like the Boeing 787 as well as the A350 extra wide body, are having greater altitude pressures compared to lower altitude pressures, which means higher pressure levels at cruise compared to some of the older aircraft, because they use composites predominantly and they can take larger levels of stresses, and therefore you're able to do that, which makes it much more comfortable for the passengers. Even in terms of the life of the avionic equipment, etc., maintaining certain pressure level ranges always is much more conducive to enhancing their lives. So internal pressurization plays a very, very critical role. I think last class, just in the beginning also, we discussed in terms of the rear bulkheads and the sealant design, etc. So all of that comes under this particular category in terms of understanding the internal pressurization, how it decides on not only the skin thickness, but also sometimes the where you're locating all your different stiffeners, be the formers or the bulkheads, etc. A lot of the decisions are made based on this. To some extent, it's actually a good thing, the internal pressurization, because remember that the main effect of the internal pressurization is the hoop stress, and then the next is the longitudinal stress, and both of these are tensile. And wherever there is compressive load, especially because if we're looking at this as a beam, this overhang, this is creating a bending in this direction. Therefore, the lower portion of the fuselage is undergoing a lot of compressive load. But because of the pressurization, there is a tensile load, and that kind of contracting, very similar to the fuel load that you talked about, how it is contracting the lift load. Similarly, the compressive load here can be contracted, and therefore buckling could probably be delayed because of the internal pressurization. So though the overall design has to account for it, there are certain reliefs also that you should be aware of, because if you're not accounting for these reliefs, you might over design certain structural components and result in a certain weight penalty because of that, which may not be necessary. Yeah. No, it slowly is dropped. So you typically have at the sea level, you have the sea level pressure itself, because you don't need to do any additional work. But as you go up, the air is released so that you reach a level of an optimal level, which is neither too low nor too high, depending on the design of that particular aircraft, and then you stabilize on that throughout your cruise.
So when we come down, does it again stabilize? We have pressure regulators basically. Once we cross somewhere around 1 kilometers, it automatically starts to open the relief valve. So as per the outside ambient static pressure. So it keeps on releasing up to a certain height, and after that we maintain that given altitude, which is given to the pressurization set. Once we start to descend, again the static pressure starts to drop. Again the relief valve tends to close, and once we go to 1 kilometer, again we bring the ambient air only to pressurize the air.
Basically, a design features, like you're saying,
Mm-hmm.
the aircraft is designed, the cabin altitude values are designed
Mm-hmm.
so that
We set the pressurization value like mm of edges. We used to set it somewhere around 700 of edges.
Mm-hmm.
It will maintain that.
Sure. Yeah. So any other questions on this? Thank you. So next we talk about how the structural components react to these loads. So these are coming from various sources. So typically a lot of this data will be given to you by the aerodynamics team and or the propulsion team, its controls team, etc. So you would then design your structural components and see how these structural components react to that. And those resultants, because we're talking about everything in a generic term, could be either forces or moments or both. And if it's moments, it could be either torsional and or bending moments that are there. I mean, if it's forces, it will be either normal or shear. And normal could be, depending upon the direction, could be either extension or compression, and you have to appropriately account for that. Many of these materials, especially when you're dealing with composites, could have very different strengths in compression and tension. So you would have to make an account for that. Sometimes the design might be such that the portions which are experiencing compression might be made of a different material compared to the those portions which are dominant tensile load kind of situation. So you might go for the different kinds of materials, as well as the geometry could also depend on that, because you want to either avoid buckling, or if buckling takes place, how you take advantage of the post-buckling scenario. Another very important point is in terms of the distinction in the shear. This many students are not usually exposed to in their first course on solid mechanics or strength of materials. So can you define what's the difference between an in-plane shear and a transverse shear? Any of you?
stress acting in the parallel of the force. The plane parallel to the force applied is the in plane.
Okay.
And in the other direction, to compensate the clockwise moment formed by this stress, is the
Yeah. So typically you would have the direct effect of most forces in the stress also will be in the same direction, or rather the opposite direction, but essentially it will be parallel to each other, right? So shear by definition is coming from a shear force, and that shear force and the shear stress will typically be parallel to each other, right? But what is the difference between an in-plane shear and a transverse shear? Because this plays a very, very critical role generally for all flight vehicle structures, but especially the thin-walled structures that we are talking about. And also, in particular, when we move to composites, because the in-plane shear capabilities and the transverse shear capabilities could be quite different for composites, unlike metals which are isotropic, and therefore their strength and stiffnesses in all directions are the same. So we need to ensure that a structure is designed such a way that the loads which are known are such that they are most of the time occurring in a particular way more than the other. Okay, to give you a hint, typically you would want it to be more in an in-plane rather than transverse. So you would want to kind of minimize the transverse loads to the extent possible in terms of the design, because for composites in particular, the transverse properties are typically matrix dominant. So, and the matrix is usually a weak thing, both in terms of stiffness and strength. So therefore, you would want as less transverse stresses as possible, and more in-plane stresses, where the fiber also contributes to some extent. So what is the difference? So that was more like a hint in terms of what is the, but this is essentially purely a geometric feature, nothing specific to composites. I'm just bringing in that in the context. But what is in-plane shear? What is transverse shear? What do you understand by, because these are fairly simple English words, I'm sure you would have come in touch with them in different contexts. Yes?
So if top and bottom surface moves in opposite direction, it will be in plane.
Mm-hmm.
And if bending happens, in case of bending,
Mm-hmm.
both the fiber top and bottom will bend in one direction.
Mm-hmm.
So that will be transverse.
Okay, okay. So it's not something to do with a general 3D model. It's more to do with the kind of models that we are going in for, typical flight vehicle structures, which are thin structures, right? So let's say a plate like this, or let's say a beam. So in that case, this distinction is, that's where the distinction comes. When you're talking of a solid, let's say brick-like structure where the length, width, and height are all of the same order of magnitude, there's not too much of a difference in terms of distinction in terms of in plane and the very word plane, I think, should give you a hint in terms of what we're talking about, and in the plane. So yeah, that's what in plane means, right? So
If I take a Z kind of a structure and I pull it from one end,
mm-hmm.
the load has to flow, and especially at the edges where it flows, the direction of shear is not going to be in the plane of application of the load.
Mm-hmm.
That is the transverse shear.
Okay,
Because
okay.
it comes because of how the load flows.
Correct, correct.
That
Right, right. Anybody else? Yeah. So to put what he said in a different perspective, you're essentially most of the shear is resisted by the skin in the aircraft. So what we call as the shear panels, and so essentially what we are talking about is a plate or a shell-like structure. Okay, it's not that this doesn't occur in beams. It's also playing a very important role there, but we don't design beams especially for that. The beams are designed more to take care of the bending, and in a generic sense, when you're talking of a 1D structure as a beam, the torsional moments and the axial loads that are there, either extension or compression. This is mostly taken by plate or shell-like structures, and when you're talking of that, it's essentially a 2D structure that we are going to be modeling it as for computational efficiency. So we are talking of in the plane means that the shear has to be in the plane. As you know, shear loads are tangential to the to whatever section that we are talking about. So in this case, let's say if it's a load like this, it's essentially parallel to the plane of the plane, this plate or shell, and therefore, as you said, the z direction. If you introduce the thickness direction as z, and then you have x and y along this. So what you're talking about is this is essentially on, let's say, the x plane in the y direction. So it's a tau xy. Similarly, load or stress coming here is essentially causing a tau xy, so tau yx, right? So this is tau xy and this is tau yx. Now these both are in terms of the coordinates x and y, which are the in-plane coordinates of this structure, because x and y are parallel to the plate, or if it's a shell, to the surface of that. Because it's a curvilinear coordinate that we'll be considering over there. So what we are talking about is within that plane, and even if we reduce this to zero thickness, which is what we'll do in modeling the reference surface or reference plane of this plate, then we are talking about something which is happening in that plane, and that is that sigma xy is typically referred to as the in-plane stress, and that in-plane stress is essentially something that can be resisted in a composite not only by the matrix but by the fibers also. But the other one is in the z direction, as you pointed out, essentially anything which is coming in the z direction, which of course will have a complementary this might look, so this is what confuses a lot of people, because this is parallel to the, but essentially what is happening is there is a thickness direction that is involved, because of which it is essentially an out of plane stress that is coming. Its complementary value will be there. But typically what is happening is most of these will be free edges, and therefore for complementary value, this will be 0, and therefore this has to end with 0. Similarly ends with 0 here. In between it goes to a large value. So that's essentially the transverse shear distribution that you could have. So in this case, it is on a plane which is perpendicular to the y directions, and it is in the z direction. So it's tau yz. Similarly, on this is parallel. This is in the perpendicular to the x direction, and therefore this is on the x phase, and therefore this is a tau xz. So tau xz and tau yz essentially in the thickness direction are your transverse stresses, and these are usually the properties through which the material resists that is typically through the matrix mostly, and therefore these are the ones to a large extent which can cause the delaminations, because remember on this phase it might be 0, but this is typically a laminated structure which is built up over many layers. So in between any two layers, because there is a tau xz, there will be a tau zx, and when there is a tau zx large enough, it can make these two layers separate from each other. Okay, so similarly your sigma zz as well. Anything? Yeah. So essentially you're talking about delamination. That's a possibility through shear. It could also be possible through peeling off, which is essentially your sigma zz. Another very important thing to recognize is that, because I said most of this is important structures, and the skin is what is exposed to your airflow and the air loads, and this the dominant air load apart from the skin friction, the more important load is the pressure load. Okay, now that pressure load that is there, most people think from a purely intuitive perspective, as soon as they see it, it should be resisted by a stress in this particular direction, which is essentially sigma zz, a normal stress. Yes, there is a sigma zz which has to counteract that, but that effect in terms of the structural behavior is much, much smaller compared to a larger effect. What is the larger effect? Huh? Hoop stresses, yes. That is if you're talking of the fuselage, and it's sigma zz is the internal pressurization that is there. Let's talk about the wing. So in the wing, you have the pressure distribution on the top of the skin. So what would be the stress that is more important than this normal stress that is happening because of a direct effect of the pressure?
It gives stress in this direction, and the component of which resists when there be a curvature of the wing. The wing will take a curvature.
Okay.
And the tension, I mean, if I just cut it into a single line, tension inside it, a component will resist the upward flow. The other
Okay, so let's put it in a little more mathematical sense. Use the same coordinates. Let's say x along the length, y along the width, z along the thickness of this. Let's say this is one of the panels of the wing, okay? Or let's say top panel on the top surface of the wing. Now there is a pressure load which is coming on this. There's a larger pressure load which is coming on the bottom surface, but that's a different panel, okay? Now let's talk only about the top panel for now, okay? So this top panel, of course, it is attached to other components at the end that gives its boundary condition. Now this is a plate that you're dealing with, or a panel. If you want to take into account the little bit of curvature, it would be a shell, but whatever it is, there is a skin friction, but that is small. The more major load, the pressure load that is happening here. And one of the ways it resists, as I said, is your sigma zz, because that is a normal stress. The pressure is actually in the zz direction. It's a applied load. Now that is being reacted by the top surface over here with a sigma zz equal to that pressure, right? But what I'm saying is that there is a much more important or larger stress that we need to be worried about than sigma zz. So which sigma is that? What would be subscripts? Excellent, yeah. Yeah. So essentially what is happening is that this sigma, even though this pressure load is directly reacted through your normal stress in the z direction, that is very small compared to sigma xx, because that is the direction in which the structure will bend. And once it bends, the stress that is going to be there is going to be a multiplying factor. We'll look into the actual expression when we derive that. But essentially, that will be much larger than the pressure itself that is applied, and therefore, that is has more potential to cause both deformations as well as potential damage if you don't design the structure appropriately, especially when you're looking at it as an isotropic material. When you look at it as a composite material, you can easily take advantage of the fact now you know that this is not a dominant stress, this is a dominant stress, so you will design such that a lot of the fibers are along the length of this parallel to your x-axis, so that the deformations are lesser and the damage or the failure is delayed as well in that particular direction. Right?
Is this basically a plane stress analysis?
It is not, because now we are saying that sigma zz is there. So once sigma zz is not 0, it is no longer a plane stress. So for it to be a plane stress problem, you should have sigma zz, sigma xz, and sigma yz all equal to 0. So now we are allowing for those sigma xz and sigma yz, which is what we called as the transverse shear stress, and we are allowing for this sigma zz. But you are right that we are approaching towards that plane stress, because we just described how sigma zz is small compared to sigma xx. You yourself told that, right? So similarly, your sigma xz, the sigma xz and sigma yz are also going to be small compared to all the other stresses, especially compared to sigma xx. And that's the reason why that's so very important, right? Okay, any other questions on this? Yeah. Yes, you're right. Yeah, so it's because of bending, because essentially what is happening is that you are integrating those forces, and that is causing a downward force, which is causing a bending about the fixed end of the wing, and therefore it is that bending moment becomes larger and larger as you go closer to this, and that bending moment will result in a stress, and that stress will have certain factors coming from the geometry, like the moment of inertia and the distance from the neutral axis, etc. So that's kind of an amplifying factor. It is, of course, in a linear model proportional to the pressure, but that proportionality factor will involve certain geometric features which makes it much larger than pressure itself, much larger than sigma zz itself. That's why sigma xx is the dominant stress there compared to your sigma zz. Even though purely from an intuitive thing, you see that you're applying a pressure which is in the z direction, so you think that should be the dominant thing, but it's by virtue of this geometry that you have that the length is large compared to the thickness, etc. If you're talking of, let's say, a cube, and then you apply this pressure, then your whichever direction you're applying that pressure, that would be the dominant load. So it's only because of either it's a plate or a beam, you would have this kind of effects because of the differences in the orders of magnitude of the lengths in the different directions. Right? So as I said, this is not something peculiar to plates. It's there in the case of the beam as well. So suppose you have a beam like this, let's say there's a beam like this. So when you have, let's again introduce the coordinate system. Let's say x, y, and z. So now, can you tell me which would be the transverse shears there in terms of sigma, the component? So is it sigma xy, yz, or zx, or which one of them? So we have two, right? So we have tau xy, tau yz, tau zx, and of course their complementaries, which is yx, zy, and xz, right? So which ones are you saying? Xz, okay. Only that one? xy? Are you sure? Why is xy? forget the loads. Let's say there are arbitrary loads in every direction. So we want to see, so in other words, I'm saying that let all of these be non-zero. But which would you classify as transverse shears and which would you classify as in-plane shear? There's no concept of in-plane here, but the transverse is very important there too. Why is it? Okay. XZ and XY, okay, that we have already looked at. Remember that X is along the length of the beam. So if you take any cross section over here, you are having the directions here as Y and Z. Okay, does that give you a hint on what is happening? So let's say this is a wing, very arbitrary airfoil cross section nonetheless. So you have a lift distribution that is there. Typically, let's say an elliptic lift distribution that you have over here. So now it would cause certain stresses, right? So once again, the dominant stress is your sigma xx like before, which is your bending stress. Above and below the neutral axis, it could be tension and compression, right? But what about the shear stress in this case? Which is the shear stress which will occur because of this lift distribution. So I'm cutting a cross section like this. It will have a bending moment, it will have a shear force as well, right? That bending moment is causing your sigma xx. That's how it is resisting. What about the shear force? How is it getting resisted? Which shear stress? Yes, okay. So it's on the x phase. Remember, this cross section I have cut perpendicular to the x direction, right? So if I've cut it perpendicular to the x direction, so it has to, the shear stress that is there, the first subscript should be along the normal direction to that cross section and the direction in which that stress is essentially acting, right? So you'd have tau xz. Of course, the way I've shown it's negative compared to what you have there. But similar to your lift distribution, you also have a drag distribution. What does that cause? In addition to tau x, xy, very good. So you would have a shear stress distribution in this direction, which is your tau xy. So here the common feature in defining your transverse stress was the fact that both were in the z direction, that is essentially your thickness direction, okay? So here the smaller dimension is your cross section, and it has two small directions and it has to be in both of them. So in general, for a general type of loading that you have, you could have it occurring in both these directions, that is your z and y directions, which are parallel to the cross-sectional coordinates. So that's essentially why these are the transverse shear stresses. And once again, if this structure were to be made out of a composite, typically the transverse shear stresses would be ones which could potentially be causing delaminations and other such issues. So this is important, just that these compared to your sigma x will be very small. Sigma xx. Remember, so the lift causes sigma xx. What stress does the drag cause? Yeah, good. So that also causes sigma xx. Okay. So both your lift as well as drag are essentially bending moments, and both the bending moments will cause stress which is normal to the cross section. Therefore, your sigma xx, and that sigma xx will be dominant compared to tau xz and tau xy. In many initial analysis, tau xy and tau xz will be ignored, but eventually to have the actual behavior of the structure, both in terms of its deformation as well as failure, it's very important to consider that. The fact that this is true doesn't mean that these are zero. It's just that these are small or very small compared to sigma xx, but not necessarily 0. And you can very easily see from the very force equilibrium that if you can write that it will have a non-zero value.
So why is the stress contracting drag is sigma xx?
Why is?
The stress contracting drag is sigma.
Okay. So essentially the drag is acting along your y direction, let's say, right? So when there is a force which is acting on the y direction, that is also going to have a distribution like this. Okay, so now that is going to make, just like the lift is going to make this structure bend like this, right? So this is going to make the beam bend this way, right? It's a straight beam like this. The drag is going to make it bend this way, right? So in either case, what is happening is that you are having that resisted by your sigma xx, because the bending moment is going to be given by the integration of all the force distribution till here, multiplied by the area on which they are acting, and then you are also having the moment arm, right? So there is one moment like this, there's another moment which is coming like this, right? So both these moments are going to essentially be resisted. Say this moment is like, so you see on the top and on the bottom I'm pulling it, right? Now this is this way, that there also I'm pushing this rear end and pulling this front end. So essentially it's once again sigma xx, positive and negative, right? So just that the neutral axis in one case will be here for the lift, for the drag, the neutral axis will be this, and the intersection of them is the point where the stress is actually 0. Okay, any doubts or questions on this? Is this clear? Okay, so this is very important, as I said, because this distinction, transverse shear stresses and the transverse forces also, because whenever you're talking of a SFD or shear force diagram, you're actually essentially plotting what results in that transverse stresses. So it's the source for that transverse shear stresses, or you can think of it in another way as the integration over the cross section of the transverse stress distribution, which is causing that transverse shear forces, right? So I think we'll start off with this. Okay, so we'll not have time to complete this slide, but we'll touch upon a few things. Let's keep the beams aside for now. First of all, why do we have shell structures? Very clearly, one of the important reasons is the weight consideration. So you want to minimize the weight. So first, from the weight efficiency purpose, you want to have a shell-like structure. Here I've shown a part of the wing along the length of the wing, just taking a particular section. Now, this question is valid not only for the wing or the tail, but also the fuselage as well, because the fuselage is also made out of a skin, which is essentially a shell, right? So we'll talk about the beams later in terms of what the role they play. For example, the box that you have here could be thought of as a beam. Already we saw the overall entire fuselage can be treated as a beam, the entire wing can be treated as a cantilever beam as well. But keeping that aside, now we talk about just the structural component, whether it is the fuselage skin or the wing skin. Essentially it's in the form of a shell. Okay, so the question is, one, yes, because of weight considerations we want to have it as a shell. The second is could be production related requirements in terms of manufacturing ease, etc., using a metal sheet. For example, if it's a metallic wing or a fuselage, you would just make it out of that. It's also easy. So let's leave these two aside. Purely from structural considerations, aerodynamic considerations, and let's say the functional consideration, the utility of an aircraft, why at all we need an aircraft, what do we use it for. From those requirements, can we arrive at this argument that we need to go for shell-like structures? So that's the question that I'm trying to ask. Purely from, let's say, starting with from a structural consideration, is there an advantage in going for a shell other than weight? There is a reduction in weight that we all know. Let's forget that for now. But why have a shell-like structure from a structural point of view? Okay, good. Excellent, excellent, yeah. So what she's essentially saying is that the torsional stiffness is going to be dictated by two parameters. One is the material parameter, which is the shear modulus. Right now we are not talking of materials, we are purely talking of the geometric features. That the geometry is what defines it to be a shell. Now, from a geometric point of view, what we need to look at for better handling of torsion is J, that the torsional rigidity has to be as large as possible. And for that, as she said, a closed cross section, you try to push the material as far outward as possible. That is what is going to help. Anybody else? Any other reason, other structural reason?
At one moment, either tension will be there or compression will be
Yeah.
there. Both will not be.
Right.
If it is a shell.
Correct.
Some eccentricity.
Correct. Yeah. So under what kind of loading? What you're saying is right, but under what kind of loading is that what you said valid? Bending, right? So just like what she said about torsion, you're telling about bending. So when you have bending, what happens is typically the axial stresses are there, what we're talking of as sigma xx over here. And the way the sigma xx is distributed is it is zero at the neutral axis, as we said, and becomes larger and larger as we go outwards. So it's very clear that if I push the material out, either in the direction of the thickness of the airfoil or the chord of the airfoil, or even if you're talking about fuselage, you're trying to push the material farther out, you're going to increase, in her case, J, and therefore Gj, and therefore for a given torque, you're going to have lesser amount of twist that this is going to undergo. And what he is talking about is EI, the bending stiffness. And again, we are talking only of geometry, so we leave E away. The Young's modulus, the material property. What we need to maximize is I, the moment of inertia. And how do we do that? By pushing the material away from the neutral axis. What she was talking about, pushing the material away from the center of twist. And these two quantities can in general be different. The center of twist and the point where the neutral axis in the two directions intersect can in general be different. We'll look at ways of how to determine that, etc. later on. But right now, whether it is the center of twist or the neutral axis, these are things that are somewhere in between. And the more you are farther away from that point in terms of the material distribution, the better, because in one case you'll increase J, the other case you'll increase I, and in both cases you'll reduce the deflections and the corresponding stresses also, depending upon how the materials are distributed. We can ensure that that is made possible as well. So that is purely from a structural consideration. So far we have looked at weight consideration, we've looked at production-based considerations, we looked at structural-based considerations. From the aerodynamic consideration, what happens? Right. So essentially, the outer contour of this is already defined for you by the aerodynamic design. That's what you want. They are not bothered about how much of thickness you have. All those things are not of a consideration at all. So they have already defined that outer boundary for you. Anyway, you have to have some material or the other at that edge. Okay. So if you have very little material there and more of it here, obviously you're going to weaken the structure. Because the aerodynamicist is asking for material over there as an interface between the air and the vehicle, you want to push the material once again closer to that. So just like from a purely structural consideration, either to increase J or to increase I, that is better behavior in torsion and or bending, you wanted to push the material out. Purely from an aerodynamic consideration also, because we want an airfoil shape, we want to push the material out and make it reasonably strong walls, strong and stiff walls that you want to have over there, right? So that's from an aerodynamic perspective. Now from a purely functional perspective, let's start with the fuselage. We'll come back to the wing later. Once again, the fuselage is also a shell, right? So it's a typically, approximately, you can think of it as a long circular cross-section, thin-walled tube, right? Now, from that point of view, from a functional point of view, why do you require a shell? Or is there some other kind of geometry which is better than a shell from a functional point of view? Excellent. So you're essentially looking at something that can occupy that, right? You were saying something? Excellent. So whether it is passenger space or the cockpit or the fuel, as he said, or the cargo, the baggage and luggage that you want, or even the control mechanisms from the pilot's end to the control surface. There has to be a path for that. So all of these have to be contained inside. So in other words, you need some space inside, right? To put your payload, to put your fuel, to put all your other accessories and other systems that are going to occupy this. These cannot be on the outside because that's going to spoil your aerodynamics. So purely from an aerodynamics point of view, we want more and more space inside. So more the volume that you can have, the better in terms of its functional utility. So this is a really very interesting and lucky situation that we have, that whether it is from a weight consideration, whether it's from a protection consideration, whether it is from a structural consideration, whether it's from an aerodynamic consideration, or purely from a functional consideration, all of these are telling us push the material out, which essentially means a shell-like structure. Yes?
So can you also say that for a shell construction, even for a transverse loading, it does not go into transfer shear state of stress?
It will still have transverse stress, just that because as we already discussed, this is very small compared to this, it will not matter much. But in terms of the distribution, the fact that it's a shell means that it's a much longer length along that direction in which the transverse shear is, especially along the chord. And that is going to be a better way of distributing that. But when you come to the lift distribution, the thickness of the airfoil is not much. So you have a smaller distance along which it has to be distributed. But the thing is, we are not having just the nose of the airfoil and the trailing edge, but also in between the spars and the spar webs. So adding up all of those areas, you still have a very good design, because first of all, the stress is small. And then over and above that, you have multiple components which are taking care of that. So there is an argument that you can make based on that as well. So one is based on torsion, one is based on bending, the other could be based on the transverse shear also. All of them are essentially telling us move the material out. But transverse shear, the interesting thing is, if you look at a rectangular cross section, the transverse shear distribution, especially when you have a free edge on the top and the bottom, you would have a parabolic kind of a distribution. So the material which actually can resist transverse shear is actually the intermediate material rather than the edge material. So that's the reason why we don't touch upon that as much, because that is not telling you to move the material out. It is actually telling bring the material in between, because that's where maximum shear stress distribution occurs in the center, and therefore have it there. So that's the reason why we go for sandwich constructions, where you have a foam or a honeycomb, and that honeycomb or foam is in between. So it takes that shear. So that's how it works. And even when you're talking of without a sandwich structure, let's say an I-beam, your flanges are taking the bending tension and compression, but the web is taking the shear. And where is that? That is in between. So in between also we need a material, and in fact these two are trying to say put the material in between, but the fact that they are so small, they don't make the decision. It's the sigma xx and the tau, which is coming because of the torsion, that can make the difference. Because that torsion that is there, that again wants you to put the material out. But this transverse shear doesn't want you to put the material out. It wants to put the material inside. Okay, so I think we just overshot the time. We'll complete the slide next class. But if any of you have questions, I'll be happy to answer further.
So in case of pure bending, whether transverse shear will be zero?
Yes, it will be, yeah. So transverse shear is purely coming because of a force. So when there is no force and there's only moment, which is the case with pure bending or pure moment, so therefore you would not have that coming into picture, yes. Yeah.
So in case of a solid beam, when you try to calculate or rather try to draw the shear stress distribution in the cross section, we take it as A say 1 by divided by I into B with the breadth of the. In case of an airfoil, what we will do? We will take the entire section as solid, or I mean it's a hollow section.
Correct.
So when you try to draw the shear stress distribution, find a it will be different in different
Correct.
places. So
Right.
how we are going to?
Yeah, very good question. So the way in which the shear is analyzed in the case of thin-walled cross sections like this, whether it is open or closed, is in terms of what is known as a shear flow. Okay, so essentially that is your shear stress multiplied by the thickness. Okay, so that is essentially what is going to flow through that, because as you rightly pointed out, there's no material in between to take the stress, leave alone shear stress, any stress. So wherever the material is there, that's where the stress can be taken at the material points, and typically there will be a flow of the shear happening through that. We'll come to all of that later on. Yeah. Okay, if there are no further questions, then we'll meet on Monday.